So I will start by writing a formula which was already yesterday. So if by chance some people will still come, they won't lose anything. Okay. Okay, so yesterday we discussed this exact sequence. So here is a cohomology group we would like to compute. Here is a space of homogeneous polynomials. And in the middle is something related to the local cohomology of, with the cohomology of the local complements. So the picture was something like that. That was V, and here we have a ball, B1, about each singular point, and we look at the local complement. And we will assume most of the time that all the singularities are isolated weighted homogeneous singularities. And because of that, yeah, the zero means that we take the primitive cohomology, we forget what comes from Pn, projective space. And when we make this assumption, I described in one of my lectures the fact that we can write down explicit basis for such vector spaces and for such subspaces given by the Hosch filtration. And so the idea is if we want to prove that this group is non-zero, for instance, it's enough to find a convenient S such that this sequence is not, such that this mapping is, sorry, so if we want to show that this group is non-zero, it is enough to find some S such that this map is not surjective, right? And how to choose such S's, you see that here it is interesting to have a homogeneous polynomial of smaller degrees. And because of that, we are interested in choosing S as large as possible. So we can choose S equals 0, and then this will cover the S equal 1, sorry. And this will cover the whole cohomology group, so it's enough to make this computation for S equal 1, and we decide if the group is 0 or not. But then we have to work with very high degree polynomials. And you have seen in the examples when all these are A1 singularities, and when n is even, you have seen that a convenient choice in this case is And so if we choose n1, then of course we get here smaller degree homogeneous polynomials. Okay, so in general, there is also a problem in understanding these spaces because in this example, they are one-dimensional, and this is very good, but they can be of higher dimension. And also, this mapping, in the case of nodes, is just the evaluation mapping of some homogeneous polynomial as the singularities. But in general, as we have seen, even for singularities of the type a to p minus 1, for p strictly bigger than 1, theta is not the evaluation map. That is, this is not sending a polynomial to the values of this polynomial in the set of singular points. And so, in general, we have also a problem how to compute this map. So, nevertheless, I will state the positive results. And then I will give you an example where one can do these computations. So you know the result, of course, but I will state it. So assume that V in P4 is a nodal hypersurface. Of degree D. And let sigma be the set of nodes. Then the fourth Betti number of V is 1 plus defect and moreover this group is pure of type 2, 2. Okay, so let me explain how you get to d minus 5 here. We have to look at this exponent here. So n is 4 minus s. You have seen here in the case of A1 singularities, we can take s to be half of okay. Minus 5, so here is something okay, so 2d minus 5 is correct, so here maybe maybe s is n plus 1, and then this will give 2d minus 5. So I have to okay, and what is an interesting remark here is that if I want to compute the defect for larger k, so for k strictly larger than 2d minus 5, then this defect is 0. So in some sense, so this is true for any nodal hypersurface in P4. And so we are just the maximal value of the defect, which can be non-zero. In many cases, this defect is also 0, but it can be 0. But after that, we are sure that always the defect is 0. And there is a similar result for nodal double solids. Let S in P3 be a nodal surface of even degree d equal to d1. Let V2 be the double covering of P3 ramified along S. Then we can compute the Betti number of this double covering by a similar formula. And we have the same result that this is pure. So the relation between the two results is very simple, because if we are in P3, assume we have coordinates x, y, z, and u here, so the surface will be given by some homogeneous equations, by some homogeneous polynomial f. And then we can add an extra variable, let's say t power 2, and look at this threefold in the weighted projective space with weights 1, 1, 1, and d1. And then, as I said, our approach works very well for weighted projective spaces, and we can get the same result. Okay, so so there are a lot of examples where the defect is positive, but I asked myself some time ago, can we construct in a systematic way an infinite series of examples with such a positive defect? And I will describe you such a possibility. Yeah? Yes? It's not easy to see. It's not easy to see, but I will come back to this point. And the same remark applies for theorem 2. That defect is the last one, which can be non-zero. After that, all the defects are 0. Okay? I will come back to this point. So some examples. So this has a Chebyshev surfaces and threefolds. And this appears in a paper of mine with Gabriel Sticlaro. Okay, so what is a classical Chebyshev polynomial? Everybody should know it because it's an interesting polynomial. So what is the main property of this polynomial? Is a polynomial of degree d. And has d minus 1 roots for the derivative, so has d minus 1 extrema, and only 2 critical values. Which are plus minus 1. So if you like, you can consider this as being some kind of trigonometric function, but in the country of polynomials, right? Because so it has a behavior a little bit, but then it goes to, so this is minus 1, this is 1, and the polynomial will go like that. So if d is, for d equal to, this should be 3 or 5, 1, 2, 4, this is d equal 5. Okay? And so using these polynomials, we can construct surfaces and threefolds. So what are the surfaces? So this is a surface in P3, given by the following equation. And this tilde here means that I take the corresponding Chebyshev polynomial in x1, let's say, and then I make it homogeneous with respect to x0. So x0 will appear everywhere here. And I do the same, roughly the same construction in P4. So you see it's not identical, but it's similar. So here x0 is hidden, but actually it is present in all these polynomials when we make the homogenization. Okay? And what is the result? We have the following proposition. The first part is for surfaces. If d is 2, d1, so if the degree is even, as in our second theorem, then this surface has this number of nodes and now other singularities, and the defect has this value. And actually, the statement for the number of nodes is it's easy to prove. And the statement for the defect, actually, we are not able to prove it. We have tested it using the Singular software. And this is true for this range. And if you like to try, you can try to find the proof. Maybe it's an interesting question. It is not obvious. The x0 is inside here because we take the homogenization with respect to x0. Okay. Yeah. Yeah. This tilde means homogenization with respect to x0. Okay? And so you see that we get a family of surfaces such that the corresponding double solids have all positive defects and defects as large as we like. And the same holds for the threefolds. This has a lot of nodes. So depending on the parity of D, we get various formulas for the number of nodes, but you see essentially the number of nodes is like a fourth power of D with some coefficients. And the corresponding defect has a beautiful formula. And again, this was obtained by computation and is valid for this range. And we conjecture that both formulas hold for any D, but we are not clever enough to prove.
What computer algebra system did you use?
I use Singular. And I will explain at some point that is quite easy to use Singular in such computations. Yeah. It's a very powerful software. Okay, and so you see we have plenty of such examples, if we like examples. And so now I will come back to the general theory. So yesterday I have constructed the Durham complex of regular differential forms on the complement, and I have constructed some decreasing filtration. And I've said that this decreasing filtration induces some filtration on the cohomology of U, and this was used in order to write, to make the polynomials appear in the exact sequences coming from topology, and so played an important role. And I also said yesterday that there is an associated spectral sequence, always when we have a complex and filtration by subcomplexes, we have such a spectral sequence. And now I will describe a little bit the properties of this spectral sequence and state a number of open questions. Okay? And this spectral sequence can be regarded as an alternative way of trying to compute cohomology of singular varieties. And it works for arbitrary singularities, but the larger the dimension of the singular locus, the more complicated the spectral sequence becomes, right? So this is an old theorem of mine, which says the following: if V is given by some homogeneous polynomial in Pn, we assume F to be reduced of degree D. And we set U to be the complement. Then the statement is that there is an E1 spectral sequence converging to the cohomology of the complement such that the first point is that the initial term, so the E1 term, has a description in terms of a complex. So this is the Koszul complex of the partial derivatives of my polynomial. So in S. And if you are not familiar with commutative algebra, this is just a complex arising from global differential forms, which I used yesterday. But replacing the differential by the cup product with df. Okay? And so to get the E1 PQ term, I have to take this cohomology group, and more precisely some homogeneous component. So everything is graded because we put the grades of the variable and of the differentials equal to 1. And using this convention, this is a description of the first term. And moreover, the limit is just a graded object of the cohomology with respect to the pole order filtration, which was defined yesterday. Okay, so these are the and I will describe this spectral sequence briefly in the case when V is smooth. So what happens if V is smooth? When V is smooth, we will get exactly Griffiths theorem. Why? Because if V is smooth, I said in my first lecture that this is equivalent to the fact that the partial derivatives form a regular sequence. And when you have a regular sequence, the cohomology of the Koszul complex is 0 except as the last term. And here, the cohomology of the last term is, if I look at some homogeneous component of the form KD, this is exactly isomorphic to the Milnor algebra in degree KD minus n minus 1. And so you see that in this spectral sequence, I have I need p plus q equal to 1, p plus q equal to n. And so the only terms here are the homogeneous components which appear. So this will be pardon?
You get a spectral sequence of negative complex.
Yes.
The hyperhomogeneous with respect to the full order. That's the spectral sequence of the one that you're talking about?
No. So yesterday I considered the complement U is a smooth affine variety. And so by Grothendieck's theorem, we can compute the cohomology using the complex of global sections of differential forms. And so this complex is denoted by AU. And on this complex, I introduce some filtration given by the order of poles. And this spectral sequence comes from this complex with this filtration.
What's the usual round differential? It's not that deep differential. So it's a different complex.
No, that is different complex. Here is the usual differential.
And you use the spectral sequence of that complex with that filtration to get what you say.
Yes. The idea is that if I take the graded pieces here with respect to this filtration, the differential from geometry reduces to this cup product. This is the idea. Okay, and you see that we have only 0 terms except this non-zero terms here. The D1 differential is something like that, so all the differential are 0. So here we have that E1 is equal to E infinity, and this is exactly Grothendieck theorem. Okay, so now let's look at the situation when dimension of the singular locus is equal to 0. So when we have isolated singularities. And then this spectral sequence looks like that. So we have a differential d1 like that, and here we have a term which is maybe so the non-zero terms in this spectral sequence are located on two lines given by p plus q equal to n, p plus q equal to n minus 1. But one has to be careful because this extends to infinity. So it's not a first quadrant spectral sequence, but we have terms all over here because in this case the Milnor algebra is no longer finitely dimensional, right? And we have all the other terms are 0 because we can show that the dimension of sigma 0 implies that there are only two non-zero cohomology groups in this complex. Okay, and an interesting conjecture related to this spectral sequence is the following: if all the singularities vi are weighted homogeneous, then this spectral sequence degenerates at E2. That is E2 equal to E infinity. So we can prove the converse. So if E2 equal to E infinity, then we can show that all the singularities are weighted homogeneous. So the two properties are surely related. And we can prove this conjecture for n equal to. So for plane curves, we can prove this conjecture. And for nodal surfaces and 3/4. But we have no idea how to prove it in general. And the advantage is clear that this means that we have just to make one computation here, and then we get the result. So this is an interest to have the generation at E2. Okay. Okay, now I would like to state some results concerning this spectral sequence. But before doing this, I will like to define an extension of the notion of defect. We define the defect for a nodal hypersurface. Now I would like to define the defect for arbitrary isolated singularities. And so I assume that D has isolated singularities. And then what I can do, I can define the total Turina number, which is the sum of the Turina numbers of all the singularities. So this is total Turina number. And I don't like to define it now, but if all the singularities are weighted homogeneous, then Turina numbers coincide with Milnor numbers, and we discussed already about Milnor numbers. Okay. Okay, and so now we have the Jacobian idea in the polynomial ring, and we consider the saturation of this idea. And by definition, this means the set of all polynomials in S such that for any I between 0 and n, there exists some power mi positive such that mi xi mi times g belongs to the Jacobian idea. And one can consider the singular locus not as a set, but as a zero-dimensional subscheme. And then these two ideals define the same subscheme structure. And this is a maximal ideal defining this structure. Okay, and so the definition of the defect. So the number of singularities, if we count them with multiplicities, the total number of singularities is given by the total Turina number. And then we have to take out the dimension of Sk divided by this ideal. So in the case of nodes, you can check that the saturation is exactly the ideal of polynomial vanishing on the set of nodes. And so this gives us exactly the same definition as before. Now I'll state some results. These are my results, and they are more recent. So if I like to compute this defect, and I like some kind of formula which can be implemented on a computer using software, and the best way to compute such a defect, in my opinion, is using this formula. So to compute this defect, we do the following thing. We look at the Milnor algebra of F and compute the dimension of a certain homogeneous component given by this formula, and take out the similar dimension of a polynomial obtained from F by a small deformation such that it becomes smooth. So F tilde is a polynomial of the same degree with F, but having a smooth hypersurface. And this is known because we have a formula, closed-term formula for such dimension. And this can be computed using singular because they have implemented the computation of Hilbert series of such quotient rings. Okay. Now, why this is related with our story? Because we can use these defects to estimate the dimension of the terms on the line p plus q equal n minus 1. So we have the following formula. The dimension okay, and the last claim. Assume n is equal to 4 and v is nodal. Then we have vanishing for the defect. For okay, and so one remark here. If I look at such a space, this can be identified with what I call the space of essential relations of f of degree s minus n. And by this space of relations, I mean the following thing. I consider all the syzygies involving the partial derivatives. With coefficients aj homogeneous polynomial of degree s minus n. And I factor by the relations coming from the trivial Koszul relations, that is from the relations coming from fi fj minus fj fi equal to 0. And so you see that having vanishing for the syzygies in low degrees, this means vanishing for the defect in large degrees. And so in a couple of my papers, recent papers, I prove vanishing of syzygies for nodal hypersurfaces, and this implies vanishing of the defect. And that was the question asked before, right? So they are not at all obvious, but they can be proved.
This wasn't known before. This property 3. I mean, this is your proof is the
Yes.
Okay.
Yes, so People didn't consider this essential relation and ask when they are trivial, so, but I think it's an interesting subject. Yeah. And they help us to understand this mysterious spectral sequence. And so we have a lot of things to do. Very good. What else I wanted to... Yes?
I'm somehow intrigued by, on the left-hand side, you just put in the sigma, which is
Here.
Just a set of points.
No, sigma with this... in general, the definition of defect is a generalized definition which I given there. And only for nodes comes down to points.
But even for nodes on the left-hand side,
Yes?
the left-hand side does not depend on happening. I mean, you could compute it for any given set of points without having an F.
Yes, but maybe that set of points never arises as the singularities of a nodal hypersurface. Yeah. Okay, so these are published results. Please check them, and if you find something not in order, I will be happy to know. But we have computed many examples, and everything fits very well, so we are confident they are correct. Okay, so now in the 5 minutes that remains, I will tell you a little bit how the spectral sequence looks for such a nodal threefolds, because you are interested in nodal threefolds, and I will describe how the spectral sequence looks in this case. So we have here these differentials, d1, 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 and we have to explain what are the terms here. And the terms here are so here we get various components of the Miller algebra. And what we get here, so using this theorem here, and this vanishing result, we get that the first group here is 0. So the first differential, we do not have to worry about the first differential. This is 0. And then this point here has a dimension exactly the defect of S 2d minus 5 of sigma. And I forgot to tell you that at the end, when I am at the term E infinity, if I make the sum of dimensions on this line, so here I should get Bn0 of V, and here I should get n minus 1, and here I should get B0n of V. The 0 means, again, I take the dimension of the reduced cohomology. And so here I have a 0. Primitive, sorry. And n is, of course, 4. And so you see that here I have a 0. Here I have something which is already what should be at the end the total dimension. And this is okay because here I get something non-zero, but this map here will be injective. And starting from this point on, both of these are vector spaces of the same dimension, which is the total in a number of V. And all these mappings are isomorphism. So there are infinite remaining going up, but all of them are isomorphism. So when I go to the E2 term, all of this will become 0. And that's why in this case, the spectral sequence degenerates at E2. And I get the known result that this number is exactly this defect. In order to make everything work properly, I have to use some results due to Morihiko Saito and to Morihiko Saito and myself, explaining the relation between these homogeneous components of the Milnor algebra and the graded pieces of the cohomology of U with respect to the Hodge filtration. So it's not elementary. This approach uses also some Hodge theory, but the Hodge theory is in interpreting these spaces as this grading and showing that we are not allowed to touch these three dots here. They are what they should be in the limit, and that's why nothing can kill classes which are here. Okay, so I guess I will stop here. Thank you very much for your patience with me for 4 lessons.
Are there any questions or comments?
Yes.
In the conjecture, the singularities are isolated.
Yes, for isolated singularities. Yes.
So what is the main obstacle to studying higher dimensions?
So if the singularities are not isolated, then suppose the singularities have dimension 1, and actually the
Isolated with the higher dimension. Because it's only 2 and the 3 case, 30
because the control we have on this relation with the graded pieces and the Milnor algebras, this becomes more complicated. And so there is a paper by Hulek and Klusterman, I guess generalizing my first approach with exact sequences and computing Milnor numbers for threefolds having a curve of singularities. This exists. And if you like to consider this approach with spectral sequences, if you have a curve of singularities, then we have an additional line here with non-zero terms. And it becomes more complicated.
If you're proving this conjecture in dimension n, you would prove that by relating to the logarithmic around complex, or you have to work with
No.
But you somehow said it related to the curve.
Yes. Yes.
I mean, if you use if you compactify U and then use,
Maybe it's possible. Yeah.
but then it would actually degenerate U1 because the substrate.
Yeah. Yeah. It could be possible.
But P in general, right, is the Hausdorff filtration. You prove that the polar filtration corresponds to the Hausdorff filtration.
Yes, when the hypersurface is smooth, it corresponds to the Hodge filtration. When the singularities are nodes, we have a good control how to compare this with the Hodge filtration. But they are different. They are different. As soon as we go, in the case of curves, they coincide because this is Delian theory, but as soon as we go to surfaces, they are different. For nodal surfaces, they are different.
Also, a question. I'm intrigued by this. This remark about the existence of this non-essential relation. So,
Yes.
if, for instance, we have defect 1, so there is just one additional syzygy, which does not come from the Koszul syzygies. So it's possible to give. I don't know. There is some kind of geometrical meaning. That
Here you see the number of syzygies. If I allow this to be large enough, it will always be the total Turina number.
Yeah.
So it's not the defect. Maybe in the beginning will be the defect, so something very small. But if I allow high degrees, then in some sense, each node will contribute with the relation. And it will be very interesting to find explicit formulas how one node creates one interesting relation. And I can do this for plane curves. For plane curves, I can write down such formulas, but not in general.